Okay, welcome. This is Dr. Morton, and this is the lecture which should have been for Friday, August 26th, but I'm doing it on Saturday because I just got so busy with Micro 1 on Friday I couldn't get it done. The first week's always a bit crazy because I have to get all the boards ready for all the Micro 1 students to pick up, and then they solder on their parts. So you'll go through that probably next spring or maybe next fall. And I think you'll really enjoy the Micro 1 course. But this is Logic Design. And we're going to talk about Chapter 2 today. Now, let me just do a couple of things here. I'm gonna switch, and we'll. So, yeah. So, here is the book. This is chapter 2, and so our objectives. One wants you to be able to convert from decimal to binary, and then from binary to decimal. I want you to be able to convert from binary to hex and vice versa, and I want you to be able to do signed binary addition and subtraction using 2's complement numbers, and understand how how unsigned binary multiplication division can be done. So note the difference between signed binary addition and subtraction and unsigned binary multiplication division. I'm probably I'm not going to cover division in this lecture. So here are the glossary things. You can hover over those. There are two videos, this one, part 1 and part 2, and they're going to cover pretty much everything I'm going to cover today. I'm just going to cover it like I would in a standard lecture, whereas these are part of the textbook, and you can click on these and watch these anytime. I suggest you watch both of these, even maybe before you finish watching this lecture, but either way, I want to do this for you. Okay, so these two basically cover the chapter, and what I'm going to cover, I'm going to highlight some of the things I want to emphasize in the lecture. Okay, so we've already talked about the difference between, and so we had a Zoom class on Monday night, which was kind of our lecture for Monday. We had the in-person lecture Wednesday, and that was kind of a special situation. This next week we won't have the in-person class on Wednesday. I will do a video lecture for Monday, Wednesday, and Friday, and hopefully I'll do your Monday lecture tomorrow on Sunday and have that posted as well. So remember, you can always look at these the lectures associated with the book. And okay, the other thing, let me just pull up the syllabus, and I think I have that here. Okay, so here's the syllabus, and if we scroll down to where we are, so I shot by it here. Okay, so here we are on the 26th, and so this is Chapter 2, Number Systems, Simple Binary Math, and I want to do that. I do want to highlight the fact that I did put in the syllabus test, the syllabus quiz. It's real simple. You'll probably get a laugh out of it. So just take your time, and if anybody doesn't have enough time, let me know. But it doesn't really. It's not going to count for much. But I do want you. Hopefully, you'll read the syllabus, and the questions in the syllabus quiz will just emphasize the things I want you to remember in hopefully a humorous way. Okay, so here we are, and we're gonna jump into Chapter 2. All right, and homework number 1 was due on Friday night, and hopefully you had enough information to answer that from the textbook and from the lecture in person on Wednesday. So that's the goal. I'm going to hopefully always be ahead of things, and so we're going to cover pretty much all you need for Chapter 2, which should cover homework 2, and I think homework 2 then it's due August 31st. Yeah, and so that'll be that's 28. That's Wednesday, right? 29, 30, 31st. Yes, that's Wednesday. Okay, So, and I'll make sure we've covered everything also on Monday. All right. Okay, so that's the syllabus. And here we are back to the book. Okay, so what I want you so again, make sure you watch these videos as well, and that'll cover the chapter. But this is I'm just going to try and establish some things. So first off, let me just say one of the things that probably should have been covered when you were in grade school is how number systems are created and number bases and all that. Believe it or not, a number of years ago, not too long after I was out of college, they came up with this thing they called the new math. So this would have been in the 70s, the early 70s, and they introduced this across the country into many grade schools, and the teachers had a cow. They had trouble understanding it. They couldn't teach it, and they rebelled en masse against this, which is kind of sad because it was really good information that should have been taught. And that's what I'm going to teach you right now. So if that hadn't happened, then they had started, if they'd fallen in line like good little soldiers and been teaching it ever since then, they would have been good at it and you would have understood this. But this got dropped and never was reintroduced. So consequently, you've never really been taught, in all probability, the basis for the number system you used your entire academic career. All right, so let me talk about that. So I'm gonna work over here for a second. All right, so if we have a number like 265.5, okay. So first off, we call this the decimal point. We call this the decimal point because this is a decimal number, and sometimes we'll write the base out here. It's base 10. Now, what that means is that we have we use the base of 10 to represent what this number actually means. Now, you know this instinctively. You don't have to think about it. You kind of understand it. You know that this first place on the right of the decimal point is tenths, which is really, in this particular number, it is 5 times 10 to the minus 1. And you know that this 5 here represents 5 times 10 to the 0 power, which equals 5 times 1, which equals 5. And you know that this 6 is 6 times 10 to the first equals 6 times 10 equals 60. And you know that the 2 is 2 times 10 to the second, which equals 2 times 100, which equals 200. So when you add all that up, you get 265.5. That's how this works. Now, you just know this instinctively, but the point of this is, and generally this is not explained. So we start at the decimal point. Working to the right, we use negative powers, and working to the left, we use positive powers, starting with 0 and increasing. And here we start with minus 1 and decrease, minus 2, minus 3, minus 4, etc. So that's how we represent numbers in base 10, but it's also how we represent numbers in every base. So for instance, let's take binary numbers, base 2. So if we write 101101.1101, now how does this work? Well, exactly the same, only we don't call this a decimal point because it's base 2. So we call that the binary point, or maybe we'll just call it the point, so it'll be correct for any base. So now we're going to have negative powers, so this is going to be minus 1, minus 2, minus 3, minus 4, working to the right from the point. And this will be 0, 1, 2, 3, 4, 5. Those are the powers, and it's going to be 2 to those powers. So for instance, this one, so let me write the whole number out. This one right here represents 1 times 2 to the 5th, plus 0 times 2 to the 4th, plus 1 times 2 to the 3rd, plus, let's see, I don't want to do this. I want to make sure we stay on the paper. So we're up to here, plus 1 times 2 to the 2nd, plus 0 times 2 to the 1st, plus 1 times 2 to the 0. Now that's all the positive powers, but we have to keep going. Plus 1 times 2 to the minus 1, plus 1 times 2 to the minus 2, plus 0 times 2 to the minus 3, plus 1 times 2 to the minus 4. Now we can cross out all the zeros because they don't do anything for us. And then we can resolve these powers, and so we basically get 2 to the 5th is 32, so we get 32 plus, this is 8, plus 4, plus 1, plus 1/2, plus 1/4, plus 0/8, and plus 1/16. So when we add all this up, this is going to be 32 plus 8 or 40, 44 plus 1 or 45, so it's going to be 45 point 1/2, which is 8/16, plus 1/4, which is 4/16, that's 12/16, plus 1/16, 13/16, plus 13/16. And if I write that out, let's see, a fourth is 0.25, an eighth is 0.125, a 16th is 0.0625, and we multiply that by 13. It's a bit much, but we already know it's 3/4, so it's 0.75 plus 0.0625, so that would be 5.218, so 0.8125. So it's going to be 45.8125. Okay, that's what we got. You see how it was exactly the same as in decimal. The only difference is, in decimal we used base 10, and in this number we used base 2. That's the only difference. And in hex we just used base 16. Now, a couple more things about bases. If we have base 10, how many symbols does it take in order to represent all the possible numbers in that base? Well, it takes 10 symbols. And the symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How about in base 2? How many symbols does it take? It takes 2. And those symbols would be 0 and 1. What about in base 16? Well, this is really interesting. This is where things started to go off the rails a little bit. So in base 16, we have, in base 16, we need 16 symbols. Well, while we can use 0 through 9, that's only the first 10. We still need 6 more. Now, our predecessors in the world of digital electronics and digital design should have come up with 6 unique additional number symbols so we could actually represent hex numbers in a uniquely and appropriate way, a unique and appropriate way. But they didn't. They were lazy. So what did they do? They looked at the ASCII character set and they stole the first 6 letters. So they stole A through F. A was 10, B was 11, C was 12, D was 13, E was 14, and F was 15. And those were the symbols we needed to represent 0 through 15 for the hexadecimal system. But there's 2 problems that I think were really made this a mistake. The first problem is that that we have A and little a, and we have B and little b. So when you write your code to recognize these as numbers, you have to be willing to realize that not everybody's going to use the capitals, not everybody's going to use the lowercase, and some people may mix them. So you have to detect a capital A and a lowercase a. And so that's the first problem. You have upper and lowercase. And the second problem is that if I write 326, you know that is not equal to a word. You know that's got to be a number. What if I write BAD or even BAD? Could that equal a word? Or could that equal a hex number? And the answer is you don't know. Somebody's got to tell you. You have to have some context to help you sort this out. So we introduced confusion where we didn't have to have it because we didn't want to create 6 new symbols. That's what happened. Maybe when you guys become senior people, maybe you can push for the creation of 6 new symbols for hex, because hex is going to be around for a long time. Now, why is hex so important? Why do you think that is? Well, here's one of the features of hex that makes it super important. If you take, and let me go back to the book. If we scroll down, I have a little table down here, right here. And notice this, I have 4 binary digits from 0, 0, 0, 0 in order, 1, 2, 3, 4, 5, all the way down to 15, 1, 1, 1, 1. It turns out that every hex digit exactly fits in 4 binary digits. Now that's not true for decimal. Remember, decimal we just have 10, so we get 0, 1, 2, 3, 4, down to 9, but then we have these extra, A, B, C, D, E, F, 10, 11, 12, 13, 14, 15, that, so the 10 decimal numbers do not fit exactly into 4 binary digits. You have six possible combinations left over. And so when we do, back in the old days when we did a lot of binary coded decimal, we had, if there was an overflow from the lower nibble to the upper nibble, we had to add 6 as an adjustment. Don't worry about that. We don't use BCD much anymore. But it was very important in the early days because we wrote a lot of programs in assembly language, and in assembly language, we didn't have all this built-in translation from ASCII into binary numbers and binary numbers back into decimal numbers and all that. All this wasn't done automatically for us like it is in a higher level language. In assembler language, we had to actually write those routines, or we had to use library routines to make it happen, and it was a lot more cumbersome. And we might not have had enough memory really even to do that. So when we had simple math things to do, like maybe a simple addition or something like that, we would use binary coded decimal as kind of a shortcut to save us from having to actually go into binary and do the mapping from decimal to binary and from binary back to decimal. So that's where that came from. But we don't do that much anymore because almost all of our microprocessors, we typically write most of our code in C now because we have a lot more memory on our embedded controllers, and we don't have to worry about running out of room and using binary coded decimal as kind of a shortcut for simple math. It was totally useless for complex math. For that, you really do have to have an advanced language, or you're gonna have to write a lot of assembly language code and do some debugging on top of that. Okay. So that's one of the reasons why hexadecimal is so important now. We can represent binary digits. Now let me show you one other thing. Okay, so let's say we have a big binary, let's say we have a 32-bit binary value. Okay, so 0 0 0 1 1 0 1 1 or 0 1 1 1 0 1 0 1 So 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, 32. So there's 32. Now, that number is really awkward. It's hard to work with this number. It's a lot easier if once you start getting into 32-bit and 64-bit numbers. If you have to write out the ones and zeros, you're gonna go crazy. What you can do instead is you can count it, and you can start with the decimal point, say the binary point, say it's there, and you divide into groups of 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4. And now I can just write each group as one hex digit. So this is 2, that's 1, that's 10, or A, and that's E, or 14, and that is B, and this is 2, and this is, there's a 1 there. This is 8, and this is 0. All right, so now my number is 21AE B28D, or sorry, 280. All right, that's a whole lot easier to work with. You can actually deal with that. You can't really deal with this 32 bits of ones and zeros, 32 ones and zeros. That's just not doable. And that's why we use a lot of hex. Now maybe one of these days we'll evolve a 32-bit code instead, and we'll have instead of 16, we'll do 32 or something like that, or 24, I don't know, something else where there's an exact fit of binary digits. But right now, this is what's being used extensively. So when you want to represent these values, we always write them in hex. If you have to deal with a 32-bit address, we write it in hex. If you have to deal with a 16-bit value, we'll write it in hex. If we deal with an 8-bit value, you can write it in with 2 hex digits, and so that's why hex is so important. Okay, now I did want to do one thing. So I wanted to just go over how we convert from decimal to binary by hand. Okay, so let's take an example. I'm going to use one. Maybe I'll do something like 37. So that's our base 10. That's 37 decimal. And if we want to convert that to a binary number, we do this little division thing. Now, I don't want you to spend, I do want you to be able to do this, but realistically, I'm not going to really test you on it. I do my students, when I used to do the in-class tests, I would test people on it, but I'm not going to do that. You're going to take an online test, so you don't really have to do this. But I want you to know how to do it, so you've seen it, you've at least seen it, you've done maybe some homework problems. That's good. All right, so let's do this. So 2 into 37, well, 2 into 3 is 1, and then what, 2 into 17 is, or 2 into 3, it goes once, and then 2 into 7 goes 3 times. So that's 13, right? No, I've got this. It's 15. I just divided in half. So half of 30 is 15, half of 7 is 3, so it's 18. All right, remainder 1. 2 into 18 is 9, remainder 0. 2 into 9 is 4, remainder 1. 2 into 4 is 2, remainder 0. 2 into 2 is 1, remainder 0. And 2 into 1 is 0, remainder 1. Okay, now it turns out this is the low order bit, and this is the high order bit. Seems a little backwards, but here's a good way to think of it. This remainder for the first division by 2 tells you if the number is odd or even. And because it tells you if it's odd or even, that has to be that has to be the ones digit, okay, or the least significant digit. So we write the number then, we take this 1 first, and that becomes our 1 over here, and then we take this 0, and then that 1, and then this 0, and this 0, and finally this 1. So in 1, 2, 3, 4, 5, 6 bits, we have this number, 1, 0, 0, 1, 0, 1, and that's base 2. That's our binary number. Now, so that's our binary number. Okay, so a couple things. What if we wanted this in 8 bits? It's easy. We just pad with zeros up here and it's fine. Doesn't change a thing. And now, what if we had, instead of 37 even, what if we had a fractional portion here with a decimal point, and then say 0.5, something like that, 37.5. All right. So then what we do, let me change this. Let me do 0.25. Okay. So we take this portion and we do it separately. We take the integer portion, divide it like we just did, but the fractional portion, we take the 0.25 and we multiply it by the base, which in this case is 2. 2 times 5 is 10, 2 times 4, 2 is 4, and 1 is 5, and 0.0. And this becomes our first digit to the right of the binary point. Okay, so our number here is 0, 0, 1, 0, 0, 1, 0, 1, and now we have point. Take this 0 down, 0. Now we multiply this by 2, and we have 2 times 0, 0, 2 times 5 is 0, and carry your 1. This is 10. Now we take this, and that becomes our second. And then we get rid of this 0, we get rid of this 1, and now there's 2 times 0. Well, that's always going to be 0, so we can add zeros out here, and we're done. Now, remember, this is 0 times 2 to the minus 1, and this is 1 times 2 to the minus 2. Well, 2 times 2 to the minus 2 is, so this is 1/4, or 0.25 in decimal. And in binary, it's 0.01. And you could add these zeros or not. Now, what if I wanted to convert this to a hex digit? Well, I'd pad out with zeros, just like that, both directions, and I count, start at the point, and I go 1, 2, 3, 4, and draw a line. Okay, so what is that? So this is hex 4, and then I go 1, 2, 3, 4, 1, 2, 3, 4. So this is hex 2, and this is hex 5. So in hex, it would be 25.4 base 16. And in binary, it's going to be 0010, 0101.01. And you can take off these leading zeros and these trailing zeros. All right? Hopefully that makes sense. Now, I want to introduce a couple more concepts and say just a little more about them. Again, I've covered these in the other videos. So one thing I want to say, this table here, I want you to go home and write that down. And what I want you to do is memorize it. You will use these hex values, these 4-bit binary equivalents for each of the hex digits, your entire career in electrical and computer engineering. So either way, you're going to need to know that, and it's going to come up again and again and again, unless you, I don't know, unless you don't deal with. Let me fix this. I think I want to be just a little bit of there. Yeah. All right. So I really want you to memorize these. You might as well do it tonight or do it tomorrow, but get it done, in the next day or two, because you'll use it the rest of your career. And it's easy. You can easily figure them out because they're in correct binary values. So you can figure it out if you're confused. But you should just commit that table to memory so you know every value on there. And I don't have any trouble remembering. For me, it's easy to remember that A is 1010. It's easy to remember that 1000 is 8 and that 1001 is 9. A is 1010. And then, I left B off the chart. Amazing. I did not see that. Oh, my goodness gracious. Well, that's crazy. Okay, so just so you know, the value for B should be 1, 0, 1, 1, and that would be B. So you can, I'll fix that table in the book, but I can't imagine how I did that. But anyway, yes, we left out B. Anyway, okay, the other thing I want to show you is what happens when you want to represent negative numbers in the computer. Well, they're really, you can think of, you know, if you were an engineer trying to develop this back in the day, you would probably have 3 ideas. Okay, so the first idea would be sign and magnitude. So you'd say the first bit equals plus or minus. If it's 0, it's plus, and 1, if it's a minus. And then you'd have the other bits would be the value. But there's a problem with this. Let's say you want to represent 0, okay? So you write 0, 0, 0, say 3 bits, and then you want it to be positive, so you put a 0 bit. But what about 1, 0, 0, 0? What would that be? Well, that would be negative 0, and this would be positive 0. But 0 is really a positive number, so there's no such thing as negative 0. So this is bad. You've got 2 representations for 0, and believe me, the digital hardware has troubles with this. It doesn't like this. This creates a lot of additional circuitry to get it figured out and get it straight. So this was a bad idea. Now the other idea, which you probably wouldn't have thought of, and that would be just to invert the number. Invert every bit. But there's a problem with this, and we call this has a name. It's an official name, 1's complement. 1's complement. So this is sign of magnitude, and this is 1's complement. So here you have a number. In this case, let's take 0 again. 4 bits, that's 0. Well, what happens if we invert every bit? We get 1, 1, 1, 1, and that becomes negative 0 again. So that's positive 0, and that's negative 0. So again, 2 values for 0, lots of trouble with the hardware. All right, third possibility, and that is 2's complement. Now, how does 2's complement work? It's basically very similar to 1's complement, except we invert every bit, and then we add 1. So let's look at the 0 example again. So here you have 0. Now you invert every bit, and you add 1. 1 plus 1 is 0, carry 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 1. And we have a 1 that carries out. Now in 2's complement math, we always throw that 1 away. We don't worry about carryouts. We only had 4 bits to start with, and we have 4 bits when we finish. And we're back to 0. So there's only one representation for 0. And it's 0, 0, 0, 0 in 4 bits. In 5 bits, it'd be 5 zeros. In 6 bits, it'd be 6 zeros. And if we try and take the inverse of that to make it negative, it doesn't work. It stays positive. So there's only one representation for 0, and the digital hardware likes that. And it makes everything work so much easier than if we did sign magnitude and if we did 1's complement. Now, the interesting thing is the first bit tells you whether or not this is a positive or negative number. If the first bit's 0, it's a positive number. If the first bit's 1, it's a negative number. Let's take an example. Let's take 3 in 4 bits. 1, 2, 3, 1, 2, 1, 1. That's 3. This equals 3. That's a positive 3, okay? Now let's take the 2's complement of that. Invert every bit and add 1. So we invert every bit, we get 1, 1, 0, 0, and we add a 1, we get 1, 1, 0, 1. This is negative 3. Now it looks funny, and the only way to figure out what that value is to switch it back. So if we switch it back, we invert every bit and add 1. So that's 0, 1, 0, 0, and we add a 1. And that makes it 1, 1, 0, 0. Oh, and that's 3. So we're back to positive 3 now. So that's how we know it was negative 3, because it converts correctly. Now, 2 points to this 2's complement thing. One is how many, say in 4 bits, how many positive numbers and negative numbers can we fit in 4 bits? Well, so how many unsigned numbers can you fit in 4 bits? So that's 2 to the 4th, or 16. And that would be 0 to 15, right? How many positive numbers can you fit? Well, or how many negative numbers? Well, remember, 0 is a positive number. So it turns out, for the positive numbers, we can fit 0 to 7. And for the negative numbers, we can fit -1 all the way to -8. So we have one more negative number than we have positive numbers, except we have 8 of each. We have 0, 1, 2, 3, 4, 5, 6, 7, that's 8. And we have -1, -2, -3, all the way to -8, that's 8. So we have 8 negative numbers and 8 positive numbers, but we have to include the representation for 0 as a positive number, and therefore we have 8 positives and 8 negatives, but we always have our negatives go one more value smaller than our positive numbers do positively, larger. So 0 to 7 and -1 to -8. This is true. What if we did 8 bits? Well, normally in unsigned, in 8 bits, we can have 256 different representations. 0 to 255. We can't have actually the 256. We can only go 0 to 255. But what about our positive and negative numbers? Well, so we can go from -128 all the way to +127. We still have 128 positive numbers and 128 negative numbers. But our negative numbers start at -1 and our positive numbers start at 0. So that's the deal there. Sorry, I'm dropping out of my frame here. Okay, so hopefully that makes sense. Okay. So 2's complement turns out to be really important. Now, one other thing: when we do math in 2's complement, we ignore carries out, but we still have to figure out if we have an overflow. Remember, you always have to make sure that your number will fit in the number of bits you've reserved. So for instance, let's say we have 8 bits. Can we fit plus and minus, say 200 in 8 bits? Well, no, because the biggest positive number we can fit in 8 bits, signed, is +127, and the smallest negative number is -128. So plus or minus 200 won't fit into 8 bits. We need 9 bits. We need 9 bits for that. And if you don't have the right number of bits, then you're going to get into trouble, because you're not. It won't fit, and it's going to give you false stuff. All right. So let me cover. Let me cover a couple more things. I want to explain why 2's complement is such a great way to do mathematics, at least integer mathematics, in digital systems. And here's the reason. If we have an adder, then we can use that adder to generate. We can use that adder to do subtractions. And here's how that works. Let's say we have a 4-bit adder. So how can we get a 4-bit adder? Well, the first thing we'll do, we'll make a 1-bit adder, and we're gonna encounter adders. Let's see. Let me check. Yeah, it's in chapter 3 that we're going to encounter this, and I'll go over it in some more detail there. But I want to tease it now. So the first thing we're gonna do is we're gonna define the equations for 1-bit adder and talk about that. And here's what a 1-bit adder looks like. Okay, you put in 1 bit of A, you put in 1 bit of B, and you put in a carry in, and you get out 1 bit of sum, and you get a carry out. Now, what you can do to make a 4-bit adder is you can take 4 of these 1-bit adders and daisy chain them together. And I'm gonna flip this around. So you can do 4 of these, and we'll just set this up. So here's our carry in, and we have a final carry out. And we have sum 0, sum 1, sum 2, and sum 3. And our input, we're going to have an A3 and a B3. We're going to have an A2 and a B2. We're going to have an A1 and a B1. We're going to have an A0 and a B0. By the way, in digital design, we're always going to start counting at 0. So our counts are always going to look a little funny. When we count to 10, we're going to do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're not going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're always going to start with 0. And that's going to be true for the rest of your digital career. Now, every now and then we violate that, but mostly we count from 0, starting at 0, up, or whatever. Okay, so now let's look at this. We have how many inputs and how many outputs. Oh, well, I didn't do some things. So what I do have is, though, the carry out here is the carry in here, and the carry out here is the carry in here, and the carry out here is the carry in here. So we're passing the carry along, and one of the things that makes this adder unacceptably slow is the fact that this final circuit won't get its carry until after this circuit finishes and sends out the carry, then this circuit finishes and sends out the carry, then this circuit finishes and sends out the carry, and finally this one gets that carry that's rippled, and so it throws in, it adds a time delay to every one of these stages, which is a problem. And that's why we don't use this in modern computing devices for adders. But conceptually, it's a nice way to think about it. It's just that when we really implement this, we do it a little bit differently. Instead of a ripple, we would call this a ripple carry adder. What we actually do is we do carry look-aheads or carry prop. We do carry look-aheads is what we do. There are other names, and there's other adders, but that's, say, one typical carry look-ahead. And we add a whole bunch more circuitry to this, and that extra circuitry calculates everything at each stage in just 3 layers, 2 or 3 layers, and that saves this ripple effect. The problem is when you get really big bit widths, like 16 and 32, 64-bit additions, then you've got a lot of hardware. So sometimes we'll break it down into chunks, maybe of 4 bits or 8 bits. We'll carry look-ahead adder the 4-bit or 8-bit chunks, and then we'll ripple those to another 4 or 8-bit chunk, and we'll build up, say, 16 or 32 bits that way. All right, so here's our adder. Now, let's say we wanted to make this a subtractor. Now, normally, let's say we have 2 values that we're going to add. We would add, say, we'll do it in 4 bits. So we'll add, say, 3, so 0, 0, 1, 1, and maybe 4. So that would be 0, 1, 0, 0. And we're going to add these up, and we should get 0, 1, 1, 1. So that equals 7. So this would be 4, and this would be 3. 3 plus 4 should be 7. Now again, we have to keep our values small so that they're going to fit in 4 bits. For unsigned, we can go all the way up. As long as we don't exceed 15, we're good. But when we start doing the sign, we're going to have to keep them even smaller because our biggest positive can be 7, and our our smallest negative can be minus 8. Okay, so we're going to do 3. Let's say we wanted, instead of adding 3 and 4, let's say we wanted to subtract 3 and 4 and see what we got. So if we subtracted 4 from 3, we should get a negative answer. It should be a negative 1. But let's do it the other way so it'll make sense for us. Let's subtract 3 from 4. Okay, so how do we do that? Well, let's say the 3 is the b value and the 4 is the a value. So for instance, this would be b3, b2, b1, b0, and this would be a3, a2, a1, and a0. A0 is the lower final one. All we would have to do to modify this adder is instead of having b go directly in, we would invert b. So we would just put a little inverter here, and we do the same all the way across. We put an inverter on the b inputs. Now the nice thing is, in the digital world, we can switch these inverters in and out. So we can make it inverted or make it not inverted, whatever we want. So that would put in the inverse of b, which would be 1, 1, 0, 0. But we want the 2's complement. Now how do we get the 2's complement of b? Well, we invert every bit and add 1. So how can we add 1 to this mix? Oh, wait a minute. What about our carry in? Why not just set our carry in equal to 1 instead of 0? And we'll be inverting every b and adding 1. And that'll make b our 2's complement number, minus 3. So b will become minus 3. So we add 1 to that. And so this equals minus 3. And now if we add a, which is 4, so 0, 1, 0, 0, to our b, which is 1, 1, 0, 1, what do we get? Well, 0 and 1 is 1, 0 and 0 is 0, 1 and 1 is 0, carry the 1, 1 and 1 is 0, carry the 1, and we throw away the carry out because when we do 2's complement math, we don't consider the carry out. When we do unsigned math, the carry out tells us that we overflowed, and it would have told us that it wouldn't fit in 4 bits. But in the case of 2's complement, we just ignore it, we throw it away, and look what we're left with, 0, 0, 0, 1. Well, if you take 4 minus 3, you get 1. And that's what we got. So we can turn this adder instantly into a subtractor by just using 2's complement. As long as we make sure we have enough bits to fit our numbers in. Because when we switch to signed numbers, then we can only put half the positives and we put half the positives because we're going to put an equal number of negatives in too. So our biggest values are going to be cut essentially in half. Although the minus number will be 1 greater than the positive number. All right. But we'll have exactly the same number of positive numbers as negative numbers. It's just that we start with 0 in the positives. Okay, hopefully that makes some sense. So that hopefully explains why we do 2's complement. Now, I want to say just a quick word about subtraction. I think I covered it in the 2 chapter videos, but I'm going to do it now. Let's say we want to have 11010.010, and we want to subtract from that, say 00110.011. How would we do that? Well, the best way to do this is we start down here, we subtract 1 from the 0, but we can't take 1 from 0. We have to borrow. So we take this 1 away, and we have a 0 there, and we put a 2 there. 1 from 2 is 1. Now, 1 from 0, we can't do that. We can't get 1 from here, so we steal this, put a 0 there, put a 2 here, then we take 1 from that 2, put a 1 there, and a 2 here. A 2 here. Oh no, a 2 here. And then we take one of those, leave a 1 there, and put a 2 here. So now we take this 1 from that 2, and we get a 1. We take a 0 from that 1, and we get a 1. We take a 0 from this 1, and we get a 1. Now we got a problem here because we got a 0. So now we have to steal this one. We'll put a 2 here. Now we take one of those and put a 2 here. We take one of those and we put a 2 here. 1 from that 2 is 1. 1 from 1 is 0, and 0 from 1 is 1, and 0 from 1 is 1. So this is our answer. And what I want you to see is that just use the number 2 up here. So yes, you're introducing decimal digits into this mathematical operation, but the truth is, you really can only do math in decimal. You're only trained to do that. And so, for instance, let's say we wanted to convert from, say, base 3 to, say, base 9. How would we do that? Well, the first thing you do is you would go from base 3 to base 10, and then you go from base 10 to 9. And the reason is because you can't do math in base 3 and you can't do math in base 9. Your brain won't let you do it. You would have to go back to grade school and go to the grade school for those that want to learn base 9, which doesn't exist. But if it did, that's what you'd have to do. So all our math really in our heads gets done in base 10. That's how we think. Now you can do a little bit of math in binary. Let me show you one more thing. What if we want to do multiplication? Well, that's super easy, and I think I do cover this in the chapter videos, as well as division. I'm not going to talk about division, but multiplication is super easy. Multiplication, you have, let's say you have 1, 0, 0, 1, and you're multiplying it by, say, 0, 1, 0, 1. So this is actually, this equals 9, this equals 5. Now let's see what we get. All right, so the first one is called the multiplicand, and the second one is multiplier. And then we have partial products coming in here. And then finally, down here we have a product. Okay, so those are the terms for multiplication. Now we know that 5 times 9 should be 45, so we'll see what we get. All right, now we look at our first multiplier digit. If it's a 1, we just copy the multiplicand, because 1 times anything is just anything. If it's 0, we put down zeros because 0 times anything is 0. So 1 times this is just going to be 1, 0, 0, 1. Now we have to shift over 1 because you have to index. It's a 0, so now we just write 4 zeros. The next one's a 1, so now we go 1, 0, 0, 1 again. And then we have another 0, so we index over some zeros. Now here are our partial products. 1, 2, 3, 4 partial products, and we just add them up. So 1 goes here, 0 plus 0 is 0, 0 plus 0 plus 1 is 1, 1 plus 0 plus 0 plus 0 is 1, 0, 0, 0 is 0, and 0 plus 1 is 1, and 0. Now, the question is did this turn out to be 45? Well, so we know this is 1, 4, 8, that would be 16, but it's 0, 32. 32 plus 8 plus 4 plus 5. So 32 plus 8 is 40, plus 44 plus 1, 45. So this equals 45. So it works. Exactly right. So you can see multiplication is pretty easy. And division is not all that difficult. It just takes a little shifting around. And all you do is compare to see if your divisor will go into your dividend, and then you put a digit up in the quotient, you put a 1 up in the quotient if it will. If it won't, you put a 0 and you shift over 1 more. Then it surely will, and you put a 1 up, and then you keep shifting. So that's how that works. Okay. All right. I think that's pretty much what I wanted to cover. Okay, we're at 54 minutes, so I'm gonna try and finish up. So you can see I talked about sign and magnitude, 1's complement, 2's complement, and then we went through addition and subtraction, and then we did multiplication and division. So you can read through this, and then you can take the quiz at the end. All right, by hitting next here. Let me say a couple of things. One, when we do these conversions from binary to decimal, sometimes we don't have terminating fractions. So, for instance, in decimal, say 2/10 is easy. It's just 0.2. A quarter is easy. It's just 0.25. Half is just 0.5, and so forth. But what about 1/3? Well, 1/3 is 0.333333. So it's non-terminating. It turns out that when you switch from one base to another, it's not unusual at all to have a situation where a fraction that terminates in one base does not terminate in another base, and so that can make it complicated. Now, how do we do this? And so, like, if you have 1/3 and you write that out as a fractional portion in decimal, you always have a small error, right? Because you can write 0.333, but eventually you stop writing 0.3s, and when you quit, then it may be a very small amount, but it's an error. It's not exactly. So the only way to preserve fractions correctly is to always preserve them as ratios of two integers. So in the case of 0.333, what we really want to write is 1 divided by 3, 1/3. 1/3 is exactly correct, and you lose no precision lose no accuracy or precision there. But 0.3333 can never be exactly accurate because you're always got a little error. So if you want to preserve that, you have to use ratios of integers. And remember, when you switch from one base to another, you can easily have small errors because there are definitely things which are nice and clean in one base, but not another. For instance, if you used base 3, 0.1 would be 1/3. So that would terminate perfectly. 0.1 would be exactly 1/3 in base 3. But we don't use base 3 much. But when you go from decimal to binary, you can have fractions that terminate in decimal and don't in binary, and you can have fractions that terminate in binary and don't in decimal. So that's good to keep in mind. All right. I think that's really probably all I wanted to cover. We're at 57 minutes, so that should be plenty. Now on Monday, I'm going to talk about I'm going to start on chapter 3, and we're going to cover all of the functions that you can make from two inputs, and I'll go over this in great detail. In the meantime, you can go ahead and look at the video associated with that chapter. All right. With that, I will stop.